So we've been doing integrals for a long time, and finally in section 6.2, your book likes to say, hey, here are the formulas for integrals. So I put them on here just so you can see them, that they're here. We've talked about these a lot. I think maybe I gave them to you at some point, but maybe not. But this is the first time they're in your book, and they tell you, hey, these are all the integrals, which is easy to figure out because if you take the derivative of this, then you get this, right? Notice they put a u value here instead of just x. And we'll talk about in a minute, like what happens if there's a composite function, kind of like the one that we just did from the worksheet, and how we can work those out. So you are responsible for knowing these. You're responsible for really knowing all derivatives, which means you really know their integrals as well. And they just like to show up every now and again, like arcsine and arctangent and E and ln, right? So if you look on the next slide, I'm not really going to go through these very much. Those are u's. They're just really squished u's, right? So if you want to rewrite those, like that, that's a u. That's a u. Integral v to the u, z to the u. The next two, I don't ever really remember those. I could think about them if I had to. But an a to the u, like 2 to the x, remember that we did have a derivative rule for doing those. The integral of ln, oh my goodness, I don't know about that one, but integral log base a. Oh yeah, that looks really ugly too. Have I used these three more than 5 times in the last 5 years? Probably not. So they don't show up very often, but every now and again on a homework question, you're going to see something, and if you don't know what it is, I have no clue how to do this, maybe go back and see if it matches one of those. Maybe on your homework this week, you might see them, but then they're not going to show up a lot. All right. So could I be wrong and they show up on an AP test this year? I could be, but I feel pretty confident saying I'm like 98.5% sure it's not going to be on the AP test. Or if it was on the AP test, it'd be on a calculator part that you could do. But here's the big thing for today. We want to talk about integrating composite functions. So I kind of just wrote a lot of stuff here, which means I shouldn't have printed these for you so that you had to write them out. But we're going to talk about integrating composite functions, and we call that integration by substitution. And really there's 2 things that you have to look for. You have to look for changing your variables. So if we're going to do a u substitution, then everything has to change in terms of u. So your dx has to change to du. And so that's what I mean by the pattern change of variable. Also, you have to just recognize what's the inside function, what's the outside function. So when we integrate, like f of g of x, as you like my words here, it's kind of like you have to sort of do a reverse chain rule. And so we've done some of these already. They've just fit perfectly. And so we haven't really talked about how to do it if it doesn't fit perfectly. But if I gave you the integral of f of g of x, it's going to have that derivative of the inside multiplied next to it. And the integral of that would just be the antiderivative of f, which we're going to call capital F. And then you leave the inside alone. And that part doesn't come to the antiderivative, right? Like it just had to stay there so that it works out. Think about, I don't know, there's one that we did somewhere on the homework that was like the integral of sine of x to the 7th, and then it had a 7x to the 6th out there. Remember that one? Something like that. And so like it worked out because you're like, oh, the integral of sine, maybe it was cosine, I don't know. The integral of sine is negative cosine, and then you bring the x to the 7th with it. That 7x to the 6th is like the derivative of the inside, and it doesn't come down to the integral, but it has to be there in order for that to work out. So that's what this notation means. So what if we change that to u substitution? So instead of saying f of g of x, what if we said u equals g of x? So then du, right, if we took the derivative of u, so du over dx would equal g prime of x. So notice if we wanted to solve for du, you can multiply dx over. So du would equal g prime of x dx. So the integral of f of u would be capital F of u. Let's see. It is pretty borderline, especially when you add the c. So that's why we only talk about f of u in calculus. No one else can handle it. What? No C sub K. We're not going to do that one. That would be pushing it. That would be too far. Today they're going to, some of your homework today is just antiderivative, like practicing the rules. The rest of your homework, I think, they tell you the U substitution, so it's nice when they tell you what U is. The harder part is when you have to figure out what your U is, and so we'll talk about that more tomorrow. Are you guys okay back there? All right, so I kind of wrote these out step by step, and I don't know if this is helpful or not. We'll do one step by step, and then we'll do a couple without the steps written out, just so that you can kind of see that you don't have to spend 2 pages doing one problem. Okay. Integrate using the given U substitution. And so they're going to give you an integral, and they're going to tell you what U is. What I hope that you do is you start thinking about, well, how could I have picked U? And U should always be like the inside function, right? Like if we're trying to make f of g of x, and we're making U equal to g of x, U is always the inside function, the function that's in something else. Yes? So how did they get x cubed plus 1 as my U? Well, it's the function that's under the square root. You see what I'm saying? So they tell you what U is, but tomorrow they're not. So just kind of maybe think about it for a minute before you just jump into the problem. Step 1 is find a U value. Today they tell us, oh look, it's right here. Tomorrow you have to find your own U. Oh, Cora. This is why you can get away with saying things like, you've never seen my legs before, because you laugh at my jokes. We're giggling with each other right now about saying you so much. Like, you. No one else cares. But I laughed, guys. I said you have to find you. No. Oh, you missed it. She said something about, I look nice today. I don't think I've ever seen your legs before. She said that earlier. Might have to go down and like funniest things she's ever said to me.
What did 6 hours say about the subject?
Some of them don't know her, and then there was this big thing of like, maybe she's really nice, and I'm like, okay, I'm basing all this off what Jake said, so maybe she is really nice, and we need to not come in thinking that she's really mean. But
Actually, we talked about her just randomly yelling at us and us getting in trouble.
some people said she was mean, some people said she was nice, some people said she's mean because she's pregnant. I don't know.
Wait, what? You had a sub yesterday?
So I'm having a sub this afternoon. I don't think we should talk about someone in such a negative way, because I don't know that she's mean, but Jake thinks she's really
Just
mean.
her daughter.
She was like,
Whoa, okay. I thought you meant like that. Her, like, actually, this is her.
Oh, Jake! You understand I'm recording this right now.
She's not gonna watch it. Actually, I remember watching. No, that's great.
Okay, enough. We're not going to say things that are bad. Okay, so if U equals x cubed plus 1, we want to take the derivative of this. And I'm going to like work it out the first time, and then we'll probably take a shortcut. But if I took the derivative of U, we could say U prime, but I want you to say du over dx, because we need a dx in the problem. And what is the derivative of x cubed plus 1? 3x squared. You got to get your derivatives and your integral straight here. Yes? We want to sub in, everywhere there's an x, we want to sub in a u, which means for our dx, we want to sub in a du. So every time you're going to multiply that dx over, I'll show you in a minute, like I just do this all in one step. Like I don't write step 2, I always just write du equals, and I take the derivative of this side, and I put dx next to it, because I know every time that's going to happen. Does that make sense? And so then here's kind of the does it match up rule, and if it doesn't match up, how do I make it match up? And so I tried to write this in steps, but I kind of struggle actually writing it out. I'm going to double page this. Dual page. Can you see that? I put get what's left by itself. I forgot by. What I mean is make it match up. I don't know how to write that as a good step. So you notice if we wanted to sub in for our u, this would be u, yes? So I'm going to write that again over here. Integral of x squared times the square root of x cubed plus 1 dx. This would be u. What I mean by step 4 is what doesn't match, like, move over back to the other side. I don't know if that makes any sense. But you notice we have an x squared and a dx here. And over here I have an x squared and a dx. So step 4, I mean get what's left outside the integral, like what's left up here, get it by itself, or move the extra stuff to the other side. Like since this is an equation, can I say that this is the same? This is the same as this. Is that a true statement? Or think about what we've been doing. We're like, oh, we don't have a 3, so we put a 1/3 out front to make it balance. Right? Instead of having to think that way now, you can just solve the equation and then you know you need a 1/3. How do I write that better? I don't know. I don't know how to write that for.
What's this actually? I don't understand this has to do with the first.
I'm trying to integrate that, okay? So I'm trying to change it to u substitution. So let's do this and see if it makes sense. Could I write this as the square root of u, because u is x cubed plus 1? And could I say x squared dx equals 1/3 du? So could I replace x squared dx, right? That substitution would be 1/3 du. Do you agree that that substitution property holds true there? The idea is you can integrate this now. Yes? Do you know how to integrate that? I'm going to put my 1/3 out front. That's like u to the 1/2 du. That would be step 6 here. Integrate. Integrate your integral. And what would the integral be, or the answer be? 1/3. If I add 1 to this, that would be u to the 3/2 divided by 3/2 would be the same as multiplying by 2/3 plus c. Yes. Because when we took the derivative of u over here, yes? When we took the derivative of u, we got 3x squared. If I want to do substitution, it all has to fit. Like if I want to do the substitution property, what I substitute in has to fit with what's in the problem. There was not a 3 in this problem, right? So how do I get rid of this 3? I just divided both sides of this equation by 3. That's where the 1/3 came from. We've been doing this all along, just with much simpler equations. But like we did it with the sign question that we did on the homework, right? We just didn't do u substitution, but we said, oh, if I took the derivative of this, I should have a 3 here, but I don't, so I put a 1/3 in front. Only on the homework question it was a 2, so we put a 1/2 with it. That's what we're doing here. And then the harder part than what we did on the sign question from the homework is you had to still integrate this. Like you had to add 1 and divide by it, which is why it's helpful to have this process. This is our first one, so we're going to do a few together. So just bear with me for a second, and we'll see if we can make it make any more sense. I have to say, when I did this in college, I did not do this step. Like I just matched it up and then said what was missing, and I put a 1/3 out front. I found these steps make it easier for people, so just humor me for a second, all right? Last step, I don't care what u is, I care what x is, so you have to sub back in, right? So step 7, this is not your answer, this gets you no credit. Okay, maybe some credit. But your answer should be 2 ninths, because 1/3 times 2/3, and then u, what was u? U was x cubed plus 1, now to the 3/2 power, plus c. If you wanted, could you take the derivative of this and make sure that you get that up there? And it will work. That if you take the derivative of this, it will work because you'll bring this down. Here, look, I'm just going to, you don't have to do this, but to check by taking the derivative, differentiating, I would have 2 ninths. I would bring my 3/2 down. I would leave the inside alone. I would subtract 1. But then I have to go back and multiply by the inside, which is 3x squared. The 2's cancel. The 3 cancels out with that 9, and then that 3 cancels out with that. So all the numbers cancel out to give you x squared times the square root of x squared plus 1, which is where we started, right? But these are more complicated, which is why just trying to figure out in your head what number do I need out front to make that balance may not be the best idea, and you still have to integrate here in terms of, instead of just saying, oh, the integral of sine is negative cosine. And so that's why I think these steps are helpful when you're doing these. So let's try another one. Anyone have a specific question for me yet before we go on, besides just, this makes no sense? Okay, let's try another one. How about this one? Look at this. Doesn't this look exciting to integrate? Again, tomorrow, like very quickly, tomorrow I'm not giving you anymore. I'm just going to give you this, and so you have to think about, I wonder what I should make u. And sometimes you pick the wrong u. You say, let's try this, and then it doesn't work out, and you have to go back and change it. But you want to start thinking, like, what is an inside function? And sine is on the bottom, so that's a good choice. It's also squared, so that's a good reason that u is sine of x. So when you get your u, step 1, take the derivative of it. So I'm going to say du equals, what's the derivative of sine? Cosine dx, because the derivative is really du over dx, so are you okay if I just put the dx next to it? What we want to happen is making things match up. If everything matches up perfectly, it's just a direct substitution. If it doesn't match up, then that's where we might have to move some numbers over. That's where we might get a fraction added into our problem. But this one I think matches up really well because this is this right here, right? So substitution, could I just replace all of this right here with du? Do you agree with that? What I circled here? Because du equals cosine x dx. True? And if u equals sine of x, what would this become on the bottom? U squared. Yes. Oh yeah, you could just put du over u squared. I just put the u squared out. I mean the du out the side, but yes. Totally could say du over u squared. Same thing. That looks much simpler to integrate than that up there, right? That's why we have u substitution. Questions on where I'm getting that? Now we just integrate it. So that would also be the same as saying u to the negative 2 du. And when I integrate, I add 1 to my exponent and divide by that, right? So that would be the same as saying u to the negative 1 over negative 1 plus c, or negative 1 over u plus c. That's really the same thing, right? So u substitution, you make it all fit. Last step, plug back in for u. U is sine of x, so negative 1 over sine of x plus c. That one's kind of tricky because some people want to say that equals arc sine of x because sine to the negative 1, but since it's a negative 1 power and not an inverse symbol, that's why you just move the sign to the bottom. Just be careful with that. It's a little tricky sometimes. Or could I make that even simpler? Oh yeah, look, I should really say that's negative cosecant x plus c. That's what the back of the book would say on that. That one wasn't so bad, right? Let's do another one. This one I could have given you before. I just make you figure it out in your head, right? That's what this one is. But I'm going to show you the process with a number. Like, where does the fraction part come in? Again, notice what they picked for u. They picked 6x because 6x is like inside the cosine, right? We don't really use parentheses there, but you could, right? It's like inside the cosine. And this is what we've been doing. Like, your book has been giving you problems like this, making you think about, oh, how could that fit? How could I find an antiderivative? But now you can just use this u substitution process if you want. Because if u is 6x, then du is what? 6dx. And so now you have options here, okay? If you don't like my whole dividing thing, I think it works out really well. But you could say, I can't just substitute in du for dx because there's a 6 there. So this is where I solve this for what matches to sub in. So that's where I divide by 6 here. And I say that that's the same as saying 1/6 du equals dx. Or what we've been doing is we've just said, oh, there's no 6 out front, so to balance it, I need a 1/6, right? Like you do that matching up in your head. But now if you just solve this so that it matches, now we can substitute in for dx 1/6 du. So that takes care of the fraction part to make it balance. So I always put the fraction out front, like 1/6, because I know it doesn't really mean anything to the problem. And then that's just going to become cosine u du, because the 1/6 is out front. Some people say on this one, I don't even need to do a u substitution on this because I can just do this in my head and I know to put a 1/6 out front, and that's okay. You don't have to do u substitution on this, but you could if it helps you. Does that help a little bit more for where the fraction came from on the first one, like trying to make it match up, solve it for that? Pretty much if you have a number here that's not over there, you're going to have the fraction in the integral because you have to make it cancel out. So this would just be 1/6 sine of u plus c. Or 1/6 sine of 6x plus c. And again, if you jump straight from this to this because you're automatically plugging your u back in, I'm okay with that too. Questions? All right, try the last one if you haven't already started. See if you can get started on that, and like there's your u, do your du, kind of like the first one that we did. See what matches, what doesn't match. I think you're going to need a fraction in this one, and go from there, and then I'll answer questions or work it out or whatever. So I think I saw most people that you move the -3 over so that you'd have a -1/3 over there. And you need to do that so that the pattern matches here, because this is our u. So we'd have u squared on the bottom here, and then x squared dx, that's all of our extra stuff. That is going to be -1/3 du, and again, it doesn't matter where you put the du. If you like it up here, if you want to keep the -1/3 in here, you can. But remember, that's just going to be a constant or a coefficient, so it doesn't really affect the integral. So I always throw that out front. You don't have to, but I just know I'm going to have a -1/3 with my problem. Questions about that? So then that's, what, u to the -2. Oh, look, it is just like our other one. So that's just -1 over u. Is that what that ends up being? Because you add 1, so you get -1 divided by -1. So that ends up being 1/3. Oh, I should write that there. All on the bottom. So 1 over 3 times u, which was 16 minus x cubed plus c. Some version of that. Could you distribute the 3 in if you want? You could. Do you have to? No? Because C is just C. 1/3 of C is still just C. Like C is just the constant. Like we just really just write C. Isn't that weird? Right. Well, because C just represents this arbitrary constant, and so no matter what you do to C, you just still make it C. In a little bit, in a day or two or three, I don't know. We're gonna ln both sides when there's a C, and then we're gonna talk about what happens with that. But really, like C just becomes C. If you had a C and a C, like it's still just C. It's not 2C. Kind of weird things happen. So that's why you just always leave it as C. Okay. I guess if you're multiplying the whole thing by 0, I don't know. Yeah. If you had a 0 in front, yes, I guess it would go to 0. It would say that. How do you feel about this? Better than when we started? Maybe. It's got to match up. Today's really nice because they give you U. When they don't give you U, like you have to pick the U that it works. And so that's where it gets a little more complicated, I think. Also notice that there's still going to be some things we can't integrate because if it doesn't match up for a U substitution or one of our formulas, like we really can't integrate it. And so there are things that we can't integrate that we have to use approximations for. So that's why we have those trapezoid approximations and the Riemann sums, because there are things that we can just approximate that we can't find the actual integrals for. 3 through 12 multiples of 3, those are just antiderivatives, like just practicing doing antiderivatives with some of those formulas that they gave you. And then starting with 17 are the substitution ones. And again, like I said, I think they give you the U's, at least on most of them. Tomorrow is day 2 of this, and it's really just like maybe a little more complicated examples, a couple complicated examples, and looking at definite integrals, and looking at not giving you U. And so it's kind of the same idea tomorrow, except for we'll have bounds tomorrow, which makes things exciting, right? Right. Emily didn't make